let's now move to the Best Paper Award, which went to Between Steps, Intermediate Relaxations Between Big M and Convex Hull Formulations by Jan Kronqvist, Ruth Misener and Tsay.
Hello everyone, I'm Jan Kronqvist and I want to thank the organizers for arranging such a nice conference. Today I will be presenting our work on Between Steps, Intermediate Relaxations in Between Big M and Convex Hull Formulations. This work is done in collaboration with Ruth Misener and Tsay. Before we start, I want to express my gratitude to the Royal Society, Svenska Kulturfonden, Engineering and Physical Sciences Research Council, and Imperial College for funding this research. Let's start with a brief background. Okay, here we consider optimization problems containing constraints of the following form, where either the first constraint or the second constraint must be satisfied, but we do not need to simultaneously satisfy both of the constraints. We refer to this as a disjunction or a disjunctive constraint, and here we assume that this is embedded in a larger optimization problem, but here we will focus on the disjunction. And we are interested in general disjunction of the following type, where we can have multiple terms in the disjunction represented by the index set D. We may also have multiple constraints in each disjunct, here represented by CL, and the variables x, they are restricted to a convex compact set, and we assume that all the functions gk are convex functions. And the main question that we are addressing here is how to encode the disjunctive constraints as a convex mixed integer problem in a computationally efficient form. And some of you may be wondering, why should you care about disjunctions? Therefore, I want to start by giving a brief motivation before we dive into the details. Let's look at a few examples of optimization problems with disjunctive constraints. So disjunctions, they naturally occur in a variety of OR applications, for example in planning and scheduling, where it is quite common that we need to choose between some options, and one option leads to some constraints, and another option leads to another set of constraints. But there are also several applications in AI. For example, k-means clustering, where we want to partition a set of observations into clusters. And this can be formulated as a disjunctive program where each data point y has to be assigned to a cluster. And depending on which cluster the point is assigned to, we get a different function to express the distance to the cluster's centroid. And for each data point, we get a separate disjunction. And we are also faced with disjunctions if we are trying to optimize over trained ReLU neural networks, for example, to perform robust verification. And here each node of the network can be viewed as a disjunction, that the node is either active or inactive. If the node is active, then the output should be given by a linear function of the inputs, which is greater than or equal to 0. And if the node is inactive, then the linear function is less than or equal to 0, and our output is 0. More details for modeling the disjunctions in neural networks are given in the following paper. But in fact, any mixed integer optimization problem can be viewed as a disjunctive program. For example, if we have a binary variable, then we naturally get a disjunction from the fact that the variable is either 0 or 1. Now, let's look at how we can model disjunctions as mixed integer problems. Now, assuming that the functions are convex and bounded on the compact set X, and that they are all well defined at the point 0. Then we have two well-known alternatives. First, we have the Big M approach, which I think you are all familiar with. Here we use binary variables to relax the constraints by shifting the right-hand side. If the binary variable lambda L is 0, then we add a large constant to the right-hand side, effectively making the constraints redundant. But since one of the binary variables must be equal to 1, we are forcing the constraints of one of the disjuncts to hold true. On the other side, we have the Convex Hull formulation, which is sometimes also referred to as the perspective or multiple choice formulation. Here, let's not go into too many details of this formulation, but I want you to notice that we need to create copies of the x variables. And we need to create one copy of the x variable for each term of the disjunction. To represent the constraints, we use the so-called perspective function, and we also introduce some new constraints. It is well known that the Big M formulation has a weak continuous relaxation, which can force us to explore a huge number of nodes in a branch and bound tree in order to find the optimal solution and verify optimality. The convex hull is the strongest convex relaxation of our disjunction, but the big M results in smaller subproblems than the convex hull, where we end up with significantly larger problems. And in the OR community, it has actually been observed repeatedly that the convex hull formulation tends to perform worse than expected. And furthermore, if we have nonlinear functions, we also end up with numerical difficulties, but these issues, they can be mitigated through conic constraints. The goal with this research has been to develop a new class of formulations in between the big M and convex hull, capturing the best of both worlds. A strong formulation, but computationally simpler than the convex hull. And this brings us to the Psplit formulations. Again, we are interested in optimization problems containing disjunctions of this type, but we need to make a few assumptions. First, we assume that the constraint functions gk, that they are all convex additively separable, meaning that the functions can all be written as a sum of convex univariate functions, and also that each disjunct is non-empty on X. We also assume that the functions gk, they are bounded over X, and that we have far fewer constraints than the number of variables in each disjunct. We could relax the first assumption. Everything works fine if the functions are only partially additively separable, but for derivation it is simpler if we assume that the functions are fully separable. The last assumption is technically not needed, but it characterizes situations where the Psplit formulation can have an advantage over both big M and convex hull. Okay, next we will go through the derivation of the Psplit formulations. And now for simplicity, we only consider disjunctions with one constraint per disjunct. However, the same technique can also easily be applied to disjunctions with multiple constraints. But then it is easy to get lost in the indices, so here I want to keep it as simple as possible. And now due to assumption 1, we know that we can write this function here as a sum of convex univariate functions. And next we will split this constraint into p parts by introducing auxiliary variables or split variables alpha. And here the first variable alpha is used to represent the first terms of this summation, and so on. And so together these constraints gives an exact representation of the original constraint. We have just split this up into multiple parts by introducing auxiliary variables. So this still gives an exact representation of the original constraint, but in a higher dimensional space. So we can think of this as a lifting step. And here alpha lower bar and alpha upper bar, these are bounds on our split variables defined as follows. So we want these bounds to be as tight as possible because this affects the strength of the continuous relaxation. We still obtain a valid formulation even though these bounds are not as tight as possible. And here we also want to avoid redundant variable copies. So if we have, for example, the same sum appearing in multiple terms of the disjunctions, or the same sum just with a scaling factor, then we do not need to introduce different alpha variables to represent this sum. However, everything works fine even with these redundant variable copies, but this may also result in a weaker relaxation. And next, we relax the disjunction by defining these splitted constraints as global constraints, so we move it out of the disjunction. And this is what we refer to as a p-split disjunction. And we can easily show that this feasible X space does not change, meaning that if we have a feasible variable combination for this set of constraints, then those X variables is also feasible for our original disjunction. And similarly, if we have a feasible X variables for this disjunct, then we can easily obtain valid alpha variables such that all of these constraints are satisfied. So we have an exact representation of the disjunction, but now we only have p variables in each term of the disjunction, where p is the number of splits, and we only have linear constraints in the disjunction. So we can think of this as a linearization of the disjunction, which eliminates numerical issues with the perspective function. So now we can apply the extended convex hull formulation by Balázs, and now we control the size of the resulting optimization problem by the number of splits. Now taking the convex hull of the p-split disjunction gives us the p-split formulation, as we call it. And I want to point out that the formulation exactly represents the original disjunction for integer feasible solutions, so this is not an approximation. And we can also show that the one split where we only introduce one alpha variable for each disjunct, is equivalent to the big M, in the sense that they have the same continuous relaxation, so it's not stronger or not weaker. And if all the functions are linear, and if we split the constraints into as many parts as there are variables in the disjunction, then we can obtain the convex hull through the Psplit formulation. But more interestingly, if we don't split the constraints all the way, but we split it into more than one part, then we can obtain a stronger relaxation than big M, but with a simpler problem formulation than the extended convex hull. To obtain a strict relation between the strength of different Psplit formulations, we need to assume that the bounds on the split variables are independent. And what I mean by the bounds being independent is that if we calculate the min or max of two components of the function, we obtain the same result as taking the min or max independently on these two components. And if this independent bound property holds, then we can show that by further splitting one group of variables, that results in a relaxation that is always as tight or tighter. And this property is summarized in the following lemma. So basically, if this property holds, then we know that more splits results in a stronger relaxation. Next, I want to show you an example. So here we have a very simple disjunction. We have 4 variables in each term, and here we have the feasible set projected down onto the x1, x2 variable space. So any point within this circle is feasible, or any point within this circle is also feasible. Here we have the bounds on the split variables given by these expressions. Here I want you to notice that these bounds, they are not independent. These figures show the relaxations of the big M or 1-split formulation, the 2-split formulation, and the 4-split formulation. So here, if you relax the binary variables and allow them to take on fractional values, then any point within these light gray areas become feasible. And here you can see that the big M formulation, it gives a weak relaxation, giving us a poor approximation of the original constraint. And with the 2-split formulation, we obtain a tighter relaxation, giving us a better approximation of the original constraint. And again, if you form a 4-split formulation, we again obtain an overall stronger relaxation. This does not form the true convex hull, but it gives us quite a good approximation of the convex hull. And some of you may have noticed that we have some additional areas here that are not included in the 2-split formulation, and this is due to the fact that the independent bound property does not hold. If we had independent bounds, then each split would result in a strictly stronger relaxation. And now let's look at some numerical results. We have tested the Psplit formulations on some k-means clustering problems that are based on the MNIST and the G2 dataset, some disjunctive test instances called P-ball problems, and for optimizing our trained ReLU neural networks. We have solved the big M, the Psplit, and the Convex Hull formulations using Gurobi, and one of the reasons we chose these test problems is that the Convex Hull formulation can here be represented in a numerically efficient form by rotated second-order cones or linear constraints. We've used half an hour as a time limit, and we've specified these parameters. And this is to avoid having Gurobi apply different strategies. Per default, Gurobi automatically selects these strategies, and we noticed that this seemed to cause unnecessary variations in the results, and we ran the experiments on a normal computer. Here are some details on the test instances. So the cluster G instances, these all originate from the G2 dataset, where we have randomly picked different number of data points with different dimensionality, and we have also tried to cluster it into different number of categories. So the cluster M instances, these originate from the MNIST dataset, where we have chosen data points randomly, but we have chosen them from either 2, 3, or 4 categories. For the neural networks, we have used the following architecture, and they are all trained to approximate the Ackley function. For each problem type, we have randomly generated 15 test instances. Here we have the average time in seconds and the average number of explored nodes to solve the problems. So for the first problem class, big M did not manage to solve the problems in half an hour, and the remaining gap is 100%. So in the right column, we have the convex hull, which solves the problem on average in 61 seconds by exploring just over 100 nodes. So here in the middle, we have different Psplit formulations, which solve the problems significantly faster than both big M and the convex hull. And the gray cells here indicate cases where the Psplit formulation solved faster than both big M and convex hull. So in the first column, we have 8 variables in each split term, which is here a 4-split formulation. And in the second column, we have 4 variables in each split term, which is an 8-split formulation. And here you can clearly see a trend that the number of explored nodes decreases quite significantly with the number of splits as the relaxations become tighter. But the tightest formulation is not necessarily the fastest to solve. And this is due to the fact that the problem grows with the number of splits as we introduce more variables and constraints. And for the other instances, we see a similar behavior, where the Psplit formulation have a clear advantage over the Big M and Convex Hull. The results are also similar for the P-ball instances. And for the larger clustering problems, we see a huge advantage of the intermediate Psplit formulations. For example, here we are able to reduce the average solution time from over 1000 seconds to just about 20 seconds. The results are also similar for the neural networks, but here the Big M formulation actually performs rather well. So for more details, please take a look at our paper. And I also want to mention that the performance for optimizing over neural networks can further be improved significantly. And please follow us on Twitter and YouTube. And here are some references. And I want to thank you very much for your attention, and I'm happy to take any questions.
All right, let's thank Jan for a great talk. And Jan is in the audience, so is in the Zoom. So if there are any questions, either put your Zoom hand up or just talk. No question from the Vienna either, it looks at the moment. So I have a question. Well, actually, it's not so much a question about your thing, but you're introducing these new variables alpha. And I'm wondering if that couldn't give more scope for learning. So if you're using a learning type solver, actually Groby may be learning now. It's not very clear. There is a question in CPAIOR. So maybe I'll defer to that question at Vienna first. So go ahead from Vienna.
Okay. So thanks for the very interesting talk. The approach seems to be very strong, right? Because in your experiments, you always improve results over the Big M or the Convex Hull formulation. I was wondering, is it always better, your approach, or are there some, is there some instances maybe where it doesn't pay off? Could you comment on that? Or is it always good to do the splits? What do you think?
Oh, thank you for the question. So it's not, in that sense, it's not completely straightforward. I would say, for example, in the neural networks, we found that the Big M actually performs quite well. And there, one of the reasons for that behavior is that the bound, when you propagate the bounds through the neural network, you tend to get weaker bounds in each layer of the neural network. So in that case, we found that, for example, the Convex Hull didn't really work at all. And what's usually worked best for those instances was actually like the two-split formulation, which was the smallest of our. So it's not, they're like, the advantage in tightness was not as great as it was for the other instances. And this is at least partially due to the fact that we are getting weaker and weaker bounds as we move forward in the neural network. So meaning even if we form the Convex Hull formulation, since all the bounds are quite weak, then the formulation itself is not necessarily super strong. So I would say it kind of depends. I would say there is a strong advantage of performing of taking one of these intermediate formulations, but it's not super clear how far you should really go. Like, should you try to make it as tight as possible, or should you be satisfied with just making it slightly tighter than Big M? I hope this at least partially answered your question.
Just a quick follow-up.
Yeah, okay. So, sorry. So just a quick follow-up on this question. So if you don't know which formulation to use, can you encode both and then run the solver?
I mean, you can. But the problem is you would basically have to run those independently of each other, or you could basically also combine two different formulations, but then there's not necessarily an advantage there, since if you split it like one step further, that formulation automatically contains the previous formulation.
Okay, so but they can't share the same variables like the formulations themselves, so that your bounds would still be the same.
I mean, you can formulate them, but like,
Okay.
but I mean, in that case, you would kind of have to solve them parallel of each other because
Okay, so they're two
issue.
separate problems. Okay. I see.
Yeah.
Okay, I was just wondering if you can share the variables and then maybe, but I guess it's not the case.
You can, and if the nonlinear bound property hold, then if the independent bound property does not hold, then there could be an advantage in that. But the issue is more if you, for example, first form of a 2-split formulation and you split that further into a 4-split formulation, then the 4-split formulation already contains all the information of the previous.
I meant combining the big M with the splits. Not necessarily like not necessarily 2-split with 4-split, but just like you have your split formulation and you also encode the big M formulation.
The thing is, if you, for example, then take a 2-split formulation, that formulation kind of contains the big M, but it's kind of hidden there. Like you don't see like the big M equations per se, but if you, for example, perform Fourier-Motzkin elimination, you can actually see like the big M constraints are there in the formulation.
Right. Okay, so very interesting discussion. And remember, there's a session 5 channel in the Discord, so we can keep going with questions for Jan.